Okay, let's go ahead and get started. First thing we're going to talk about is cation stability. We'll run parallels to radicals, then we'll look at anion stability, and we'll add another tier to this. So, one of the things that you're going to find you need to do is to be able to look at an individual molecule and predict something about its reactivity. All right. That reactivity in most cases is going to be due to what? Charge. Charge is usually the easiest place to look for reactivity. If you see a charge, you need to neutralize that charge. That's the whole goal. Right? If you don't see a charge, the other place it may be buried would be in differences in electronegativity. Okay? So be aware of what pieces you're looking for. Okay? And in all of those cases, what you're ultimately doing is looking for either sources of electrons or sources of a lack of electrons, which I know sounds kind of weird, but that's what you're trying to do. Because when we're dealing with organic chemistry, it's just about moving electrons around from one place to another. So if you can find where electrons exist, you can get through that a little bit cleaner and easier. Okay? So, we've got 4 structures up here. All of them are potentially unstable. What makes them unstable? They all have a charge. Is that charge different? It's still a positive charge. For those one of you that said yes, why are you saying yes?
Because the molecules or the atoms attached to the central charge atom are different.
Okay, so it's deciding on where we see that initial difference or that initial ranking. Okay, initially we start, all right, trying to get you to start small and just focus. We got a positive charge on a carbon, no difference. So what do? We move outwards to see if there's a difference. Because if there is no difference, then this is a dumb question. Okay? If there is a difference, I now need to understand what that difference is and how does that apply to the reactivity of the molecule. Okay, so as we work our way further out, we do and see that there is a difference. We've got some carbons or some hydrogens on the outside of that. What we want to know is how does that affect the overall material. Okay, so the first thing that we should go through and do is evaluate what makes all of these structures unstable. So what is that? I've already said this. It's the charge. What charge? Positive charge. How do I make the positive charge more stable? It needs electrons. So one natural instinct that a lot of people tend to do, which is fine, is say, okay, well, I have electrons. I'm going to give electrons to it. That stabilizes it. True, but that same source of electrons can be used to stabilize all of these. Okay? So that doesn't help us out. We don't want to look outside the structure. We want to look within the structure. Okay, so what happens when we look within the structure? Well, we want to find electrons. Where's the closest source of electrons to the positively charged atom? Okay. The closest source is going to be the bonds. Each of those lines happens to represent 2 electrons. So we could go through and draw those 2 electrons in over the top of it. What's the issue that we'll very quickly find? All of them have 6. So if there is no difference, what do? Move to the next atom out. Okay, so you keep moving out until you find a difference. So in that very first case, or the very top one, we see that we have hydrogen, hydrogens all the way around, versus an extra carbon in there. So really all I'm trying to evaluate is the difference is not so much the hydrogens, but hydrogen versus carbon. And that sole difference is right there. Everything else is identical. So what is the difference between carbon and hydrogen? So we heard electronegativity and I heard valence electrons. Okay, when we went through and dealt with acid-base strength, we went through and ranked them according to certain things. We started with charge, then we moved to, we went to size. Okay, we looked at an atom effect and we looked at size before we looked at electronegativity. We want to do the same thing here. So what's the difference in size between carbon and hydrogen? Carbon is bigger. How does it get bigger? Do protons contribute to size? It's more electrons. The nucleus, yes, is bigger, but that's a very small percent of the overall atomic size. So we're looking at more electrons. Well, how many more electrons? Let's start to actually quantify this. Right, how many electrons does carbon bring in? Right, I'll accept that. How many electrons does hydrogen bring in? 1. So if we did that comparison, which of those two cations would be more stable? Okay. Bottom one with 4 or the top one with 1? Okay, so if we go back to stability, what were we trying to do? Neutralize what charge? Positive. What do we need to neutralize a positive charge? Electrons. That 1 and the 4, what were the units on those? It's 4. Which one's going to stabilize the positive charge more? The bottom one, because there's now 4 electrons to stabilize the positive as opposed to just 1. If we continue to work our way down, you'll notice that we have to expand our viewpoints when we compare, because we look at that next one down, it's still just carbon. Okay, so instead of looking at it as just the atoms, what we could go through and do is just total, I'm going to have to step back too far, how many electrons around it. So in that first case, how many electrons total around the carbocation?
6.
Okay, we can bring in 6 because of the bonds. Okay, so we get 6 electrons. How about the next one? We still get those 6, and then your carbon brings in a couple extra. In all honesty, I don't know how you guys are doing your math, so I'm not sure what the next number is going to be. We're going to stick with 12. 12 electrons. And the last one? 15 electrons. Okay. You guys got the right pattern. That's ultimately all I really cared about. Okay. Is that we're just adding more and more electrons on. So now if we look at the whole picture, which of those carbocations is the most stable? The bottom one. Well, we can't go through chemistry saying the bottom one is more stable. So we come up with a name for it. What's the name? Tertiary, because that references how many carbons are connected. So tertiary is more stable than secondary, because there's now 2 carbons there, which is more stable than primary, which is more stable than, thank you, please propagate that, zeroary. Okay? So what we're trying to do is go through and just see how that stabilization effect carries through. Okay? What happens if we switch that up to a new molecule? Let's look at this guy now. What kind of carbocation do we have now? There's a couple answers with it. So in black, what do we have? What kind of carbocation? Okay. The official big grand answer, which of course it sounds like everybody was waiting to figure out, was allylic. What's the other answer we could contribute to this? That's not a hand. I was like, that's the first hand I've seen in class. How many carbons are connected to our carbocation carbon? 1. So it is primary. So we have a primary allylic. What did allylic reference? It's proximity to that double bond, okay, to that pi bond. So we have a primary allylic. Where this becomes a bit more interesting is that if we now try and drop its rank ability, okay, its stability, where is it? If we went based off of the primary, we might say it's probably darn close in stability to the primary. Where is its stability? It's somewhere about down here. Depending on who you talk to, they might actually rank it more stable than a tertiary. Well, so something different has to be happening here, and that difference has to come back to that allylic. What is that allylic thing doing? Resonance. We can now move the electrons to physically stabilize that positive charge. That carbon is now no longer positive, and now when I'm looking at the overall molecule, the effective positive charge for that molecule is half as much as it was before, because there's now 2 structures. Okay? So resonance will do a lot for stabilization. Okay? It can also destabilize structures, as we'll look at in a second. Okay? But before we move on, everybody okay with that? So if you see resonance, Usually a big signifier that you're looking at stabilizing. Okay? Yeah.
Resonance pretty much turned into the same thing, just
So resonance, by definition, will always turn it into the same thing. Okay? It's just where the electrons are located within the molecule. And when we deal with resonance, your structure is pinned. You can't pick it up and turn it. Okay? Or flip it or do any of that fun stuff. Right? I'm pretty sure I didn't. Oh, I did want to do that. So we got our names that go along with this. One of the chemistries that we won't see to the very end of the semester, but we can look at radicals. Radicals are very similar to carbocations. Why? What is a radical? I'm hearing charged. Okay? That middle section right now, or second row, is now radicals. Where's the charge? Okay. Let's move to the first row, or first column. Where's the charge? Where's the charge in that first column? Central carbon. How do you know the central carbon is charged? What charge is it? Positive. Yeah, it's charged. There's a plus sign next to it. Look back to the radicals. Are they charged? No, they're not charged. Okay? But what is weird about them is that they have an unpaired electron. Okay? So ultimately, an unpaired electron is going to act very similarly to not having any electrons in an individual orbital, which means our radicals will act similarly to carbocations. So if you see or asked a question about radical stability, it's the same kind of explanation you'd go through with carbocations. Exact same. Okay? So in both those cases, our most stable is our tertiary, or our allylic, or potentially benzylic, all that, our resonance stabilization. Okay? So then the trick is, what happens when we move to this last example?
the opposite.
Okay, why would it be the opposite? What makes this column unstable? The negative charge, which means it has too many electrons. So what's going to make it more stable? We want the fewest electrons around it. Okay, well, if we go through and do our comparison, the one with the fewest electrons around it is our zero area. So we get the reverse of that kind of system. Okay? Resonance does not always make it more stable. Okay? Because I could take resonance and I can move electrons towards a negative charge. What is that going to do? Make it more negative or less negative? More negative. Well, is more negative stable? No. So sometimes resonance will actually make a structure more reactive. Okay? Typically when we're looking at resonance, we're looking at carbocation or positively charged species. Why would resonance always make carbocations more stable?
You can distribute the charge.
You're distributing electrons towards a positive charge. Like charges or opposite charges cancel out. We've got a neutralization of the charge, it becomes more stable. When we've got an anion, now we run into an issue. If we move negative towards negative, that makes it more reactive. Okay? So you're just trying to see that balance in what's happening with the electron motion. Let's get your question good enough, at least for the moment. Okay. Last part of whatever this chapter was, I think chapter 6, they make mention of a zwitterion. Really common in biochemistry. So when it shows up in biochem, everybody freaks out and says, oh, we got to do all these calculations. And all organic chemistry is horrible. Ultimately, the zwitterion and all these charges and calculations that you do with it is actually gen chem. It's actually 152. And what we're looking at is a balance of the conjugate base with the acid and how does the pH affect the overall solution. So you're just looking at what happens when I change the pH. Well, if I have a very low pH, what happens?
Yeah, more berries.
I have more H plus floating around. So anything that's a source of electrons is going to pick up an H plus. So if I'm at a low pH, I would expect to be in the protonated state for that individual functional group. But if I'm at a very high pH, what happens? Okay, I'm very basic. Okay? And that base is going to do what? pull hydrogens off of my structure, and I'll have the deprotonated state. So one of the things that you would have to be familiar with are what are the various protonation and deprotonation states for an individual functional group. Right? That's partly what we do in organic chemistry, so that if you look at this functional group, what functional group is that? Carboxylic acid. Is that in its protonated state or deprotonated state? Protonated state. Okay? So if it's in its protonated state, should I put another proton on it? No, it's already there. Okay? So what you're just trying to do is the balance between that. Where does this become important? Amino acids in biochem. Okay, so you will see it if you have to take a biochem class, come back and haunt you. There's some nice, oh, apparently I did not save that edit on my slide. That is unfortunate. And it's jumping all over the place. I had just put in a new edit on this, saying that if your pH is lower than your pKa, so you'd have to look at the pKa for your individual functional group. If the pH is lower than your pKa, you should be in the protonated state. If your pH is bigger than your pKa, you need to be in the deprotonated state. So if we go back and take a look at our structure, the carboxylic acid has a pKa of what? I'll accept 2, but that's not the answer I wanted to hear. 5 is better, usually about 4. Okay. So if we're at a pH of 1, what's the relationship between pH and the pKa? pH of 1, pKa of 5. pH is less, so I need to be in the protonated state. What happens if I move up to a pH of 7? Now I'm in the deprotonated state, so I remove the hydrogen from the structure. So it's just looking at a balance of your different protonation states all the way through it. Okay? So there is a question in the homework. It does show up in the textbook as kind of an applied section of this material. The other big thing that's kind of fun to say out of it is zwitterion. Anybody speak German? Nobody? Really? I was going to say, I think I remembered hearing someone say that Zwitter was twin. Oh, actually, no, I did look it up. It's hermaphrodite. Okay, so you have a hermaphroditic ion. It has both charges. Really straightforward and simple. Okay, kind of neat. So that's all that's happening. So if we take a look at our individual structures, that middle one is our zwitterion, because the overall charge is neutral, but it has both charges in it, both a positive and a negative. Okay, so you may hear reference to a zwitterion in future classes. After that, what we're really doing is moving into chapter 7. Okay, and I'm getting a lot of delay here. Remember our arrows. Okay, the most important one that you guys are going to keep seeing is your curved arrows. And I'm pretty sure my computer's dying. The curved full-headed arrow showing the transfer of 2 electrons. Right? We're going to keep using that. Get used to it. So you have to know how to use those. When you move into biochem, depending on where you're taking it and at what level you're taking it, they will expect you to understand something of what curved arrows mean, because that's how you're moving from, say, an amino acid to a protein. You can look at that balance of electrons, how they shift, to predict changes in structures. Okay? So, resonance and mechanisms. We've got our rules now for moving our electrons. Okay? We will always move negative to positive. Okay? We went through and looked at definitions of acids and bases. Why did we look at those definitions of acids and bases? Because that gives you something that you can potentially zero in on. If you see the molecule such as this guy, you see that show up in a question, what did you just find? Say that louder. Acid. You've got an acid. Well, what does an acid do? Donates a proton. What charge is a proton? H+. Where's there an H? We got 2 of them. How does it become positive?
The electrons go to the oxygen.
by the electrons that it's sharing with that oxygen going solely to the oxygen. You've now broken off an H+ that could potentially go out and react with something else. Okay? So one of the things that could be in there would potentially be what? A base. What do we know the base needs to do? Accept the proton. Well, what does the base need to have to be able to accept the proton? Electrons. So now you can start whittling down that structure and look within the base structure for a source of electrons. What if there's multiple sources of electrons? Then what do? You start to go through according to your base strength rules. Okay? Is one charged? Look at electronegativity. Look at size. Okay? Those same things that we went through and did with our acids, we've got to go through and now do with the bases. Okay? So you have to keep going back to those rules. Okay? The biggest addition that we're bringing in this chapter is mechanisms. And ultimately, all this chapter is trying to do is summarize all the possible mechanistic steps. Okay? After that, every new chapter that we move into will look at one or two of those types of reactions and say these are the mechanistic steps involved in each of those. Okay? And once we understand a mechanistic step, there's going to be certain repercussions that come out of that. Okay? Perhaps we form a carbocation. Well, if we have a carbocation, it better be stable, otherwise it can't form. So we go back to deciding ranks of cation strengths. Okay? So it's a lot of back and forth between all of these and keeping those definitions straight. It requires practice. Okay? So here's our definitions again. Super, super, super important. I will explicitly ask for these definitions on this next exam, and you will also see it, I guess, implicitly on the exam as well. Having you look at an individual structure and say, that structure can act like an acid, okay, or that structure can act like a base. Okay? Questions on those? Last one I want to draw your attention to, mainly because there was a weird question in the homework about electron-rich and electron-poor. It sounds like that's pretty universal, that everybody had a problem with it, so I'm probably going to go through and just delete it. It's just an odd question. So if you look at an individual molecule, what you're trying to do is look for sources of electrons or look for places that are lacking electrons. So in your electron-rich atoms or molecules, you're looking for lone pairs. Okay? But sometimes, or lone pairs in charge, but sometimes those are hidden from you. Remember, lone pairs are often implied. They're implied, you don't see it. Okay? You have to remember that they are there. How do you know how many lone pairs are supposed to be present? You may not see the charge either. You drew tons of Lewis structures at the beginning of the semester, and you memorized the particular patterns for individual molecules. Or if you didn't draw the tons of structures, there was that chart where I said if you have carbon with 3 bonds, these are the charges you'd expect to see. You have that memorized. Otherwise, you're shooting in the dark. Okay? And that will become increasingly more difficult and frustrating for you. So make sure you've got those basic patterns memorized. Okay, so if we don't see the lone pair and we don't see a charge, the next thing we can look for our electron-rich would be an ionic bond. Okay. Why an ionic bond? An ionic bond, kind of said nicely, has charge. It has ions. So by definition, it's got charge within it. Okay. And so we can hide an electron-rich atom by putting a metal next to it, because metals are classically very not electronegative, for lack of a better description, okay, which makes the other atom much more electronegative. Okay? And if we go through and look at these, your negative charge is your most electron-rich, your ionic is probably next, lone pair is probably last, okay, as far as your electron-rich sources. Electron-poor, you're looking for an electronegative bond, a covalent or polar covalent bond, typically to hydrogen. Okay, that's your big signifier for electron poor. You will also see formal positive charges pop up. That very clearly is going to be electron poor. The other one is having a halogen connected to a carbon. Why might that be electron poor? Halogens are all very electronegative. What are they going to do to the electrons in that carbon-halogen bond? Take all the electrons away, leaving the carbon without electrons, making it positive or electron poor. Okay? So that's a large section of this material, or this chapter is identifying those pieces. So electron poor versus electron rich. If we take a look at our top example, that NH2 would be a good example of electron rich. How do we know that? It has the negative charge. Okay. And if we were trying to look at an individual reaction, put these labels in there, because those labels can help us, we would probably do that one first. Why? Okay. Because it's already charged. Right? There's an electron rich, which means what does the other one have to be? Electron poor. All right, so at least initially we can assume we're not going to give you two electron rich molecules because that becomes more difficult to play with. All right? So that means we have to find some place that's electron poor within that molecule. Where's our electron poor region there? The hydrogen. Why is the hydrogen electron poor? Because the electronegative oxygen is sucking electrons away from it. That makes that hydrogen very electron poor. Okay. Questions that naturally arise out of that. If you guys don't come up with one, I'll come up with one. The electron poor molecule, at least as SmartWork has it labeled, is this whole thing. Okay. And that hydrogen, yes, is electron poor, but it becomes electron poor by doing what? By being bonded to the oxygen, which took the electrons, and now the oxygen is electron rich. Okay. It's only electron rich once the hydrogen's been removed. So now we're looking at electron rich over here. Okay. Up until that point, it hasn't officially gained those electrons, so it's not officially electron rich.
So it just has the partial.
It just has the partial charge. And that partial charge can also be misleading. Okay, so be kind of aware of that. Bottom one, kind of ignore the middle part of that. I just didn't have time to cheat and draw it all the way through. That was way too much erased. What happened? Where's our electron poor, electron rich? Okay. So we could jump to the being of the product, and that's actually kind of important. This molecule is extremely electron rich. It's so electron rich that just making this, the guy that made this molecule, actually gets named after him. The whole reaction does. Okay, because it's kind of rare to have a carbon that's electron rich. Okay, but that's in the product. What about our starting materials? Where's our electron rich site? There's a hint. It's our magnesium is electron rich. Why did you guys not say the magnesium being electron rich? Just curious. I think I heard someone say it. Magnesium typically is positively charged. When we see magnesium, it's usually magnesium ion, in which case it is +2. Is this magnesium ion? How do you know that? There's no charge written in the upper right-hand corner, and another tip-off is that we see 2 electrons there by that lone pair. Okay, so our magnesium is our electron rich, and our electron poor is actually the other molecule. Okay? So there's supposed to serve as just some quick examples for that. We don't need those words. We could bring in some more examples. Not too concerned about those, at least at this point. So what we have now, this I don't think is actually summarized like this in your textbook. This is me. There are 5 primary types of reactions that you will see this semester, and then we keep kind of going back to these 5 same primary types throughout the year. All right, so you need to be familiar with these and being able to identify them at whim. So if we draw out a reaction, you should be like, oh, that's an elimination reaction. Or another reaction, oh, that's an addition reaction. So you need to be able to find the common patterns within each of these so that you can identify it. Why? Probably by the end of second semester, you will have a vocabulary of roughly 200 different reagents, maybe 300 different chemicals and reagents. Okay? Those chemicals and reagents react very differently with starting materials or different starting conditions. So you need to be able to recognize what type of reaction it is, and then maybe you'll know the reagent right off the bat, because maybe there's only one reagent that does an addition reaction. Not true, but let's just say it was. All right, so if you know it's an addition reaction, you now know it's just that one reagent you need. You've now eliminated 200 other possible answers. Okay? So recognizing the type of reaction is critical. So within these, what's happening? That very first one, an acid-base. What's happening in an acid-base? The only thing that's changed location is a hydrogen. So it's a transfer of a proton or a hydrogen ion between two of these. What happens in the case of a substitution? And yeah, you may be seeing some weird symbols pop up in there, but ultimately that doesn't matter. We don't care what the symbols are. Look at what changed. What changed is we went from left to right across the substitution reaction. We swapped Lg for NuC. Right? Anybody know what those two terms are? Leaving group and nucleophile. Those are going to be very important things to understand eventually. Okay, but at this point, we again just want to recognize what's happening. In an elimination reaction, what things changed as we moved from reactant to product? The hint, I'm pretty sure it's not only partially listed up the top. What's happening in an elimination? Okay, we see the formation of a pi bond. What's that? And the leaving group went away. Is that it?
You lost 2 sigma bonds.
It says 2 sigma bonds lost. So far, we've only identified 1. There's a hydrogen that is also removed. Okay. Why are the eliminations particularly tricky? How often is that hydrogen actually shown? Usually very, very rarely. So you have to watch out for that. If you see a pi bond forming, you have to already be thinking a hydrogen was removed from the structure. You now have to find the proper hydrogen to remove. All right? Addition reaction. What's happening in an addition? Okay. We lose the pi bond and we gain 2 sigmas. 1 to a nuke and 1 to an elect. What do you think those stood for? Nucleophile and electrophile. Okay, so it's recognizing those patterns. The last one is our radical reactions. We'll probably spend one day talking about those at the very end of the semester. Okay. They typically classify as both substitution and addition reactions, and they do just weird stuff. Okay. Questions about those? Okay. So now we move into mechanisms. Ultimately, what we're trying to deal with our mechanisms is look at elementary steps. Okay, you all remember the kinetics chapter from 152, right? One of your favorite chapters. Dealt with all the calculations, unimolecular, bimolecular, all that fun stuff. Okay. With a rate law, how do you calculate what step makes sense, all of that. Okay. We are kind of looking at that. Kind of. Okay, so it will come back, and you will see some questions that are at that kind of level in your homework, but it's only one, I think. You won't see that show up later on. You will see the interpretation of what it means. Okay? So when we're looking at our mechanisms, how does an individual reaction occur? We just looked at 5 different types of reactions. How do those reactions occur? When do they occur? Right? And it's really broken into 2 things. Either breaking a bond, and in this case, for the 4 primary, I can't count, 4? 1, 2, 3, 4. 4 primary reactions. It's going to be heterolytic bond cleavage. What does heterolytic mean? So there's our bond. How do I break that bond between A and B heterolytically? Cleavage in this case just means breaking. It's all going to come back to hetero. Both electrons are going to move to the atom that is typically more electronegative. So in a heterolytic bond cleavage, what's the natural result? Well, we'll have A and B again, but now no bond between them. What happened to the electrons? B has the electrons and a negative charge, and A is positively charged. So that's what's happening with a heterolytic bond cleavage. Right? Bond formation, since we're already specified in our cleavage is happening heterolytically, our bond formation is all going to happen heterolytically as well. Right? So if we looked at bond formation, what we would then say is that B now attacks A. Right? And we now share the electrons between them, and we now have our bond back again between A and B. Okay, so those are two main things that are happening. It's now just a question of when they happen, okay, and what they happen with. So I went through and numbered these. I think we set it up as 7 different types. You guys should all be familiar with these because you all watched that video, right? All right. So within this, in a simultaneous situation, heterolytic, our bond cleavage and bond formation happens at the exact same instant. We would show that by showing all of the arrows happening in the exact same step. Okay? Heterolysis is now just the breaking of the bond. Just saying, whoop, let's just break it. Okay? Followed by potentially coordination as bond formation. Okay? What happens if we then change what we're working with? If we look at an addition reagent, okay, or addition reaction, we aren't making and breaking sigma bonds, we're making and breaking pi bonds. So that's going to change the type of materials we're looking at. And that's where we get this nucleophilic and electrophilic additions versus electrophile and nucleophile eliminations. Okay? So let's take a look at some of these as examples. In our simultaneous situation, in fact, let's just go ahead and do this. You got 3 reactions there. Add some arrows. Okay? Make sure that you show everything that's happening as you go from the left side to the right side in a single step. And we have an acid-base reaction. Oops. So, how does it occur? What do you need to do? Okay. Our oxygen-hydrogen bond needs to break, okay, and we need to form our nitrogen-hydrogen bond. So what we would now do is add our arrows over the top of this to make sure we're showing how what moves. The electrons. So the very first thing that we should go through and do, or at least that I personally go through and do, is find the best source of electrons. Where's the best source of electrons? Okay. The bond between the OH, I can accept that, but that's not the one I would have looked at. But let's deal with that, because for sure those electrons are doing something. Where are those electrons going? To the oxygen. Okay. So that's now explaining the breaking of a bond. Okay. The natural instinct for most people to go through and do is now draw H+. What you're doing by that is drawing the product. Okay. So then if you added the next arrow into this, you're saying it happened in 2 steps, not 1 step. Okay. So we want to make sure that that bond breaking happens at the exact same instant as the bond forming. So where does the bond forming occur? Between the nitrogen and the hydrogen. And we have to make sure that our arrow accounts for that appropriately. Where's the electron source? The lone pair on the nitrogen. Should probably stop using an eraser. And we will show those electrons sharing with the hydrogen. We are not showing the motion of the atoms. We are showing the motion of the electrons. Because these 2 arrows are now in the exact same reaction step, as witnessed by seeing only 1 reaction arrow, I'm saying that these things are happening at the exact same instant. So we get heterolytic bond cleavage and bond formation all at the exact same instant. Once I've added the arrows, I can then draw the product and show the results of what those arrows mean. Right? That's where charges will show up. That's where loss of lone pairs may show up because we've made a new bond. Okay? So we show the arrows to say this is the action of what's happening, but we really only see the beginning and the end. Okay? Next reaction, what happened? We've got a substitution. Okay, what happened? Bromine was substituted with iodine. So we need to again go through and show how this is all happening. Okay. So since we're using a mechanism and showing curved arrows, we want to find our source of electrons. Where's our source of electrons? Everybody's, why bromine and carbon? Seriously? I mean, you're right, but typically it's easier to look at the iodine. Why the iodine? It's already negatively charged. And you're not wrong, so keep doing what you're doing, but the iodine is charged. It's typically easier to find. There's our source of electrons. That's our electron-rich atom. Where's our electron poor? We could say the sodium, but in the iodine bonds to the sodium, and our result would be nothing. That's pretty boring. So try again. The carbon. Why the carbon? Okay, so there's a couple big answers there. One, hearing someone say it is positive. Why is it positive? It's got bromine attached to it, which is electronegative, sucking the electrons away from the carbon. That makes that carbon positive. There's another big reason why we should be attacking that carbon. Look at your product. Where's the iodine attached? To that carbon. That's a pretty valid reason for having the iodine attack the carbon. Okay? But now how many bonds would that carbon have? Would have too many bonds. There's two hydrogens, a carbon and a bromine already there. If we make a fifth bond with iodine, that's a problem. So we have to break a bond. What bond do we break? The carbon-bromine bond. Where do those electrons go? Why do they go to the bromine? Bromine is more electronegative. Yet another reason. Carbon had exceeded its octet. If the electrons went back to the carbon, does that fix the exceeded octet? No. The electrons need to be pushed away from the carbon. Okay. How do we know this all happened in one step? There's only one reaction arrow. If I wanted to show this split into two steps, I would show two arrows, two reaction arrows. Last one. Okay. Our base attacks the hydrogen. The electrons go in to make the pi bond, and we kick out Lg. And do a very good job balancing this, or showing the lone pairs on that Lg. Okay. Again, tricky reaction, because we're making that pi bond. One of the arguments that can be made with this is that we aren't actually making the pi bond. We're having the base remove a hydrogen, which then means what happens to the carbon? It becomes negatively charged. If the leaving group, or the Lg, leaves and takes the electrons with it, what charge does that carbon become? Positive. So it would look something like this. What is the relationship between that charge structure and the one right above it? There it was. It's resonance. Okay. So we don't have to make the argument that we're making the pi bond right away. We can show that negative charge. Okay. That's kind of a shortcut-ish. So if you have a problem seeing the pi bond form the two anion, or form the two charges and combine them later. Okay. So when we do a simultaneous reaction, you'll notice that we've got a couple symbols that popped up in there. Saw the term of Lg for leaving group. That's our issue with breaking a bond. It leaves with the electrons. That's why it's called a leaving group. Okay. You may see nuke or base show up. That's in reference to nucleophile or base. Why are they typically colored the same and grouped in the same category? They both donate electrons. So as far as their chemistry goes, they're almost identical. The only thing that's different is a nucleophile donates its electrons to... Electrophile is a fair answer, but I was hoping for something a little bit more vague, or less vague maybe. Anything other than hydrogen. Because as soon as it donates its electrons to hydrogen, it's now no longer a nucleophile, it is a base. Okay? So it's just a question of figuring out exactly what to call each of these things. So our nucleophile or base will always make a bond, okay? But in the process of making a bond, you almost always have to break a bond. Not always, but it does tend to pop up. So we could look at our SN2 again. We just walked through that. Where's our nucleophile? Which molecule donated electrons? A or B? A is our nucleophile, which means B is, actually that one's a little bit weird. We can call that an electrophile, I'll accept that. B contains what? Yes, it contains chlorine, but the chlorine is our leaving group. Okay. B is most commonly referred to as a substrate. Okay. Questions on that?
So we would consider like the leaving group is always a substrate?
The substrate contains the leaving group. Substrate and leaving group are two different things. The substrate has a leaving group within it. Yep. So we got a new problem here. Where's our leaving group? Or our substrate, or our nucleophile for that matter. Keep going.
And then the base, yeah, the base would be the carbon.
Base.
Would be the carbon. Yeah, or this is
Our substrate, and then the NH3 is our nucleophile. Why throw this example up here? How big is the nucleophile relative to the leaving group? Okay, relatively small. Okay. That size is ultimately irrelevant. Okay, but very commonly you end up seeing your nucleophiles being the big piece and your leaving groups being the small piece. That's not necessarily true. Okay? So watch out for that. Your leaving group will always be the group leaving with electrons. Your nucleophile will always be the group sharing electrons. The order is irrelevant. We can start with the nucleophile on the left, or we could have the substrate on the left. Depends what we want to do. Okay?
I have a question. Does the
Yes.
SN2 step like mean something specific? Like
Yes.
does that always refer to?
SN2 refers to very, very specifically up at the top of the board, substitution, nucleophilic, technically bimolecular, not just two. Okay. Where have you heard the term bimolecular before? Gen Chem in 152 talking about kinetics. Okay, so it will come back. We could look at the same deal with our eliminations, same kind of idea. Everything's happening in one step. You'll notice that we have more curved arrows happening in this step. That's fine. We can do multiple curved arrows in a single step. Okay, that is perfectly valid. Okay. If it's going to be of the elimination type 2 situation, it has to happen all at once. Okay. You'll notice the slight change is we're no longer looking at a nucleophile, we're looking at a base. Why are we looking at a base? Because it reacts with the hydrogen, not with an electrophile. Okay? Again, you'll notice some new examples or odd examples. Our leaving group in that top case happens to be something that is relatively large in comparison to our nucleophile, which is pretty tiny. Or sorry, our base. Thank you for catching me over there. I heard you. Okay. The other one that I wanted to address in that bottom case, why might that bottom case be tossed in here? What type of pi bond are we making? What's the result of this reaction? A triple bond. And everybody goes, oh, well, a triple bond's not an elimination reaction because it's not a double bond. The elimination reaction is the formation of a pi bond, not a double bond, of a pi bond. Okay? So I can eliminate more from an alkene to make an alkyne. Okay? So be aware that that does pop up. After that, we can break it down into our other steps. So now what we're doing is ultimately the same thing as we just did with the SN1 or the simultaneous reactions for our substitution and our elimination, but we can now break it into two steps. We can do a heterolysis followed by a coordination. Well, that result is going to still be the same thing as the SN2, our substitution, but it's going to have happened in a different order. Because what we end up doing in our first step is a heterolysis where we've broken the bond, and then we can follow that up with the reaction with a nucleophile. And that nucleophile, if it comes in and attacks, we now have the formation of our new product, the overall result being a substitution reaction, but I've now broken it into two mechanistic steps. How do I know there were two mechanistic steps? There's two reaction arrows. Okay. Where the first step of that was our heterolysis, the bond breaking. The second step was the bond formation. Could we ever do bond formation before bond breaking? Why not? It would exceed the octet. We can't do that. Okay? So more examples of all that bond breaking stuff. Should we go through all of those in detail, or is the video good enough? Good enough. Works. Intermediates, carbocations. Okay, remember our stability of carbocations? We had zeroary, primary, secondary, or tertiary. Okay. Which one's the most stable? Tertiary is more stable than all of the others, at least in this list. Okay, and this one's stable. The zeroary and the primary are so unstable that if we're asked to do a reaction and we show the formation of a zeroary or primary carbocation, it is an awful step. Okay, which means that mechanistic step doesn't work. So if you're trying to predict a reaction, you never want to form a zeroary or primary carbocation. Just avoid it altogether. Okay. The next issue we run into is what happens if a secondary carbocation is near a tertiary position. Okay. What we end up with is something known as rearrangements. Okay. These are always kind of tricky, and you got to watch out for them. If you see a carbocation, you should immediately be thinking, this is ridiculously unstable. I need to do whatever I can to stabilize it, because that's what the molecule is doing. And the molecule will do that by either saying, nope, I'm not forming, hence the zeroary or the primary, or in the case of the secondary, it will look within its structure itself to see if it can collect electrons from some other place, the net result being a shift of the positive charge somewhere else. Okay, in that molecule. And as long as the result takes us from, say, a secondary carbocation to a tertiary, that is a legitimate step, and we would expect that to occur. So we have to watch out for that popping into our reactions whenever we see carbocations. So we've got a general reaction shown below. How could we add some curved arrows into this to show it? It's a bit challenging.
You would take the bond from the shift group and move it to the other bond.
So we want to take those electrons and we want to somehow get them over to the other position, which theoretically that will start coloring in a second here. Yeah, it just died. Okay, so what we're going to do is take the electrons between the carbon and the shift group, and we want to move them over to the carbocation. We're not moving them into a bond, because we're not trying to make a pi bond. What we're trying to do is take the atom with its electrons and put them on the other position. Let's see, are you working again? Yeah. So we're going to take those electrons and we're going to move them to the carbocation. Okay, this is one of the reasons why I personally like the online homework systems. They're very nitpicky with how you use your arrows. If you try to draw this out by hand, I have no clue where you're trying to draw that arrow. Because most commonly what we'll end up seeing is something like this. Is that going to the bond? Was that even a double-headed arrow? I don't know. Okay? It's virtually impossible to grade. The online homework system will get nasty nitpicky with it. Okay? Your electron source, in the case of the rearrangement, is coming from the bond. So what you will do is start your arrow at the bond, and you need to show it going to the atom. Okay? Which on the homework will actually go all the way down to the atom. So you need to see those positions highlighted. Okay? Not the same thing as the other arrows we've shown, because we've now taken electrons from a bond and shifted it to an atom where the bond's not even attached. So it's a really weird process. Allegedly a British thing, though I'm not positive on that. The other option is to go in and throw in a little curlicue. Okay? Because now it's a weird thing. It's not just a standard arrow pushing. We're trying to signify that there is something odd happening here. That's the rearrangement thing. So you might see that little curlicue thing. I think it's kind of a little cutesy thing, so I usually do it when I do my arrows. Okay? The net result is that what happens? The atom that was positively charged just gained electrons, so it becomes neutral. But the bond between the shift and our carbon, okay, all of those electrons went over to the other position, which means what happened to that carbon? It's lost electrons. It becomes positively charged. So one of the things that students tend to try and do is move the positive charge. Well, the positive charge looks like it's jumped from one place to another. You can't show that arrow. Why not? You're not moving electrons by moving a positive charge. A positive charge is by definition a lack of electrons. Okay?
Why would it do that if you've got one positive charge, the other?
So it comes down to stability. So here we've got some more specific examples. If we take a look at the carbocation in that first example, what type of carbocation do we have? It's a secondary carbocation because it's connected to only 2 carbons. Right? And what they're showing with that arrow, so we're going to take the electrons from the bond and we're going to give them to our carbon. So we've now taken those electrons, ripped them up, dropped them back down now on this side. That carbon started positive, but it's now gained an electron, so it's now neutral. What happened to the other carbon? It's now positively charged. What type of carbocation is that one? Tertiary. That is now tertiary. Which is more stable, secondary or tertiary? Tertiary. Tertiary. That's why the shift occurs. Is because you end up forming a more stable intermediate. Everything's striving for that stability issue. Okay? Does it have to be a hydride? No. Does it have to be a methyl? No. It can be pretty much anything can shift. Okay? But the 2 most common ones are hydride shifts and methyl shifts. Why do we not call them hydrogen shifts?
Because it's a negatively charged.
It's hydrogen shifting with 2 electrons, which is known as a hydride. Hence the term hydride shift. Okay. The most common ones that you'll see will be numbered as a 1-2 hydride shift. What's the 1-2 in reference to? The relative position of where your hydride started and where it ended. Okay. So it's an attempt at nomenclature to specify how far it jumped. Questions on our rearrangements? Just a sec.
Okay, so for the 1-2 methyl shift, right?
Mm-hmm.
If you are talking about stability, how then do we have to shift it? Because the one on our left, structure on our left side, looks like it's stable to me. So
How many carbons are attached?
so 1, 2.
So it's a secondary carbon.
Okay.
And in the other case, it's
Oh, okay.
tertiary. Okay, so you will always run a reaction to form the more stable product. So if we form that secondary carbocation, you have to be concerned about it rearranging to the tertiary.
It means the other carbon, like the carbon 2, so will be unstable right there. It was stable.
Yes.
That's what I wanted to say. It means that all our references on the
All our emphasis is on the carbocation. I don't care where it is. I just want to make that carbocation, whatever carbon it is, the most stable carbocation I can. Okay. Is it possible for me to do secondary to secondary to secondary to secondary to tertiary? And the end result is a more stable cation, right? Would I expect that to occur? Is there any driving force to go from a secondary to a secondary? How about a secondary to a secondary? Or secondary to secondary? Okay. Not going to happen. Okay. So even though the tertiary is more stable, there's so many other steps that would have to happen first that are not favorable that never occur. Well, if they can't occur, I can't get to that last tertiary intermediate. So when we're doing rearrangements, it's a single rearrangement. It is possible to string together multiple rearrangements, but each of those steps must be progressively getting more stable. Right? You can't reverse stability. Just a sec. So there was 1, then 2, then 3. Yes?
So how far can the hydride and methyl shift? Can they only move
As
one position?
far as you're concerned, one position at this point. We'll talk about rearrangements potentially second semester in more detail.
It just seems like the 2 carbons that are involved are not 1 and 2, but 2 and 3, because they're in the middle, right?
Yes, so it's not the nomenclature numbering, it's the location of where the shift started from and where it ended. That's why it's 1, 2. So it's not the naming of the structure, but it went from this location to this location. I'm going to call that 1, 2.
So then, okay, then just call it,
Yeah.
doesn't matter where it is, it's just call it 1 and 2.
Yeah.
So you could potentially start with a 0 area and then move up to 1, 2, 3.
So theoretically, if we could form a zero-area carbocation, it would rearrange to a primary, which would rearrange to a secondary, which would rearrange to a tertiary, allylic, benzylic, all that fun stuff. But what did we say about the zero-area? Doesn't form. And our primary also doesn't form. We also run into an issue. It's kind of impossible to go from a zero area to a primary, because a zero area is connected to how many carbons? None. There's no way that you could shift it to another atom in the chain because there is no chain. But theoretically, the idea is there.
You can go from
Primary to secondary to tertiary. Okay. Still stepped reactions. We can do an electrophilic addition. So what we are now doing is an addition reaction. In the case of an addition, we're reacting a pi bond. So our pi bond then needs to react with a positively charged atom. In this case, in that top case, it's the nitrogen of the nitro. Well, the nitrogen of the nitro is positively charged, which by definition makes it an electrophile. So what we have is an electrophilic addition, because we add an electrophile to a pi bond. Right? We do also end up with an intermediate, and you'll notice that we have that positive charge popping up. Okay, why has that become obnoxious? As soon as we have a carbocation, we should be thinking rearrangement. Right? So the stepped reactions will generate intermediates. Those intermediates can then do all sorts of other nasty chemistry that we didn't want them to do. So we do have to watch out for that. Okay? The bottom example has also been classified by your textbook as an electrophilic addition. Any questions about that bottom example in particular? As a hint, I have a slight issue with that being referred to as an electrophilic addition. What did the pi bond act as? Source of electrons, good. Where did those electrons go? They were shared with hydrogen. So what did this molecule act as? A base. What did the other molecule act as? An acid. Why is it getting called electrophilic? I think it's because they didn't want to come up with an acidic addition. So it's pretty much the same thing as an electrophilic addition, except the electrophilic atom is hydrogen as opposed to a positively charged atom. Okay, so kind of watch out for that. That will get classified as an electrophilic addition.
On the top structure,
Mhm.
the top reaction, would the carbon on top that's positive in the product, would that one, the one to the right of that, the carbon to the right, if that were to, would that shift to be the more positive charge? Would that be more stable?
So
Bring on?
I will reserve that for talking about that after class. No. It won't do a hydride shift. The other thing that we got to watch out for that's kind of tricky on these, you'll notice that in both these reactions, the pi bonds were symmetrical. Which meant that when we put on that electrophilic group, it just went on to either one of the carbons. It didn't matter which one, because we got the exact same result. What if our structure was not symmetrical? Would it then matter where it was placed? Yeah. So we would then have to evaluate why would we put it in that individual location. Right, so we'd have to look at other intermediates. For instance, resonance. So we could look at our first worst resonance structure. I think I got that right this time. Okay. to then decide where it belongs. In this case, we don't have to stress about it. Okay. We can do an electrophile elimination. So now we're eliminating something from the structure. The piece that we're eliminating happens to be, again, what they're classifying as an electrophile, which I also find odd, because what are we eliminating from the structure? Hydrogen. So it's, again, really kind of an acid-base reaction. Okay. Does it have to be eliminated as hydrogen? No. It's just very commonly is hydrogen. Okay. And ultimately, all this is the complete reverse of the previous reaction. So what we've done in this case is the opposite of the electrophilic addition. Right? Results in the formation of the pi bond as opposed to the loss of the pi bond. Sorry, questions on that?
So are we expected to know that it's an electrophilic elimination versus an acid-base reaction?
I would accept both answers on a test.
Okay.
We've still got two more stepped type reactions. We've got the nucleophilic addition. So it's still an addition reaction, so we would still kind of expect a pi bond to be involved. But in this case, it's a pi bond that is very polar. If we go back and look at the electrophilic addition, it's a carbon-carbon pi bond. Well, a carbon-carbon pi bond isn't polar. Okay? The nucleophilic addition requires a polar pi bond. Why might it require a polar pi bond? It has to do with our electron source. Right? In the electrophilic addition, our pi bond acted as the electron source. Right? In the nucleophilic addition, what does our pi bond act as? The electrophile. It acts as the place that's being attacked by a nucleophile. So it's just a change in the environment of what's happening about our pi bond. Right? Is it being attacked by something? Nucleophilic addition. Is the pi bond attacking something else? Electrophilic addition. Okay, so it's all about how does the pi bond act. Questions on this one? Okay. Nucleophile elimination, ultimately the same deal. Okay. Except the nucleophile elimination is super, super common after a nucleophilic addition. Okay. They are almost always partnered with each other. And that's because that intermediate that was generated after the nucleophilic addition, this guy right here, is incredibly unstable, okay, and will break apart very, very quickly, but it breaks apart in such a way that it gets you to a new product, okay, or a different product. That change is ultimately why we would then tie these together. Okay? And in that result, you'll notice that what ends up getting kicked out? Chlorine, which we could say was a leaving group, but in this case, what's your textbook referring to it as? It's a nucleophile. Okay, nucleophile elimination. We've eliminated a nucleophile from the molecule. How do we know it was a nucleophile? Because it's negatively charged. Right, we're starting to get to the patterns of finding negatives and positives. Okay, just a little bit, right? Everything we do is going to center on this. So we have to know what these individual steps are so we can string them together. Okay. These last two, the nucleophile elimination and the nucleophilic addition, account for most of the second semester OChem. Okay. And arguably all of the chemistry necessary for biochem comes from those two mechanistic steps. Okay. So they're really, really important. Theoretically, you're taking second semester if you're going to move into biochem. Okay. So we'll spend the last couple minutes here taking chapter 6 material and now turning it on our mechanisms. Okay, so what we've got here is a reaction, reactant to product, with how many mechanistic steps? We got 4 mechanistic steps. So what I want you to go through and do is add curved arrows to every one of these and label each of the reactions according to what type of mechanistic step is happening. Right, for instance, I will give you one of these steps. Which one step do you want me to give you information on? Okay, the first step. Yeah, that's what you get for waiting too long. That first step, our electron source is our oxygen, sharing electrons with H+. We end up forming our new sigma bond. That type of reaction was an acid-base reaction, so I can write acid-base underneath this. If we wanted to get super nitpicky on this, we could say that this species acted as our Bronsted-Lowry base, and this was our Bronsted-Lowry acid. Right? Theoretically, you should be able to go through and do all of that labeling. Right? What you would then be able to do is go into your energy diagram and try and predict what's happening in each of these cases. Right? So if I take a look at those two species, I've got a reactant 1, and I'm going to use I1. Since I don't know how my energy is going to shake out, I'm going to draw my reactant 1 somewhere in the middle. Okay, and I1. Well, now I want to do, where's the energy of I1 relative to reactant 1? Well, I1 is charged. Reactant 1 is not charged, which means I1 should probably be higher in energy. So there's my I1. I now want to connect them up. There's my first step. Okay? Go through, play around with that in the next, minute.